Dear colleagues, let me introduce myself. My name is Vitaly Kuznetsov and represent National Meteorological Academy of Ukraine. My other co-authors are from the Dnipro State Technical University, Mr. Kamensk, Ukraine, the Dnipro University of Technology, and Les Konchar Dnipro National University. One of the branches of our research team's scientific interest is the study, design, and optimization of very dynamical systems. Today, these systems are used in different industrial applications in mechanic and electric engineering, communication, robotic, and so on. The implementation of these systems is based on well-known and modern cybernetic approaches by using modern IT technologies. One of the rapidly growing model concepts is Internet of Things concept. The Internet of Things describes physical objects or their groups that are embedded with sensor processing ability, software, and other technologies that connect and exchange data with other devices and systems over the Internet of Other communication networks. The field has evolved due to convergence of multiple technologies, including computing, commodity, sensor, increasing powerful embedded system and machine learning. Traditional field of embedded system, wireless sensor network control system automation, including home and building automation, independently and collectively enable the Internet of Things. In the consumer market, IoT technology is most synonymous with product pertaining to the concept of the smart home, including devices and appliances such as lighting fixtures, thermostats, home security system and cameras, and other home appliances that support one or more common ecosystem and can be controlled via devices associated with that ecosystem, such as smartphones and smart market. The IoT can also be used in a healthcare system. There are a number of concerns about the risks in the growth of IoT technologies and products, especially in areas of privacy and security. Security is the biggest concern in adopting Internet of Things technology, with concerns that rapid development is happening without appropriate consideration of profound security challenges involved and the regulatory changes that might be necessary. Most of the technical security concerns are similar to those commercial services, workstation, and smartphones. These concerns include using weak authentication, forgetting to change default credential, uncrypted message sent between device, SQL injections, man-in-the-middle attacks, and poor handling of security updates. However, many IoT devices have several operational limitations on computational power available to them. These constraints often make them unable to directly use basic security measures, such as implementation firewalls of using strong crypto system to encrypt their communication with other devices, and the low price and the consumer focus of many devices make a robust security patching system uncommon. We offer improving security of IoT system by using secure data transmission channels, which are designed by using chaos theory. This theory is interdisciplinary scientific theory and branch of mathematical focused on underlying patterns and deterministic laws highly sensitive to initial condition in dynamical system that were thought to have completely random states of disorder and irregularity. Small difference in initial conditions, such as those due to error in measurement or due to rounding error, is numerical computation, can yield widely diverging outcomes for such dynamical system, rendering long-term prediction of their behavioral impossible in general. These can happen even of these system and deterministics, meaning that the future behavior follows a unique evolution and fully determined by the initial conditions, which no random element involved. In other words, the deterministic nature of this system does not make them predictable. This behavior is known as deterministic chaos. Nowadays, a lot of dynamical systems which generate chaotic oscillation are known. Attractors of some of them you can see in slide number 3. It is clear that these attractors are different and thus system dynamics for the various systems are different as well. Moreover, due to the unique properties of these systems are very hard to predict the system attractor on the system design stage. We offer to avoid this drawback by using hypercomplex number to define chaotic dynamic and transform it into the desired subdomain. You can see problems that we solve in our paper on slide number 5. One can consider this problem as complex problem that allow define chaotic dynamics in the hypercomplex domain. First problem, performing system transformation. Second to the third problem, and showing the use of a considerate approach by performing transformation for well-known Lorentz system. The fifth problem. It is well-known fact that the free motion of dynamic system can be chaotic if the system order is none less than 3 and system has at least one nonlinear function. That is why we use nonlinear ordinary differential equation in matrix form to describe system dynamics. In this case, vector of state variables y is defined by using its projection in different axes. One can get a similar vector by using hypercomplex number. Resulted hypercomplex number shows system state at the point in some n-dimensional state space, which axes are defined by using real and imaginary unit vectors. Since system order and can differ from hypercomplex space dimension, and we use zeros to hide unused dimensions. This approach allows us to define one hypercomplex nonlinear function g, which components gy can be defined by using components fi on initial dynamic system and rewriting matrix equation of considered system as a first-order nonlinear differential equations, which you can see in slide number 6. Such an approach makes it possible to reduce system order and solve only one differential equation instead of several ones if a classical approach for system modeling is used. Thus, we solve the first problem of this paper. Due to the use of the hypercomplex number system dynamic is defined as vector motion is nth dimensional hypercomplex space. It is clear that this vector can be easily transformed by using classical shift, rotation, and compression transformation. Moreover, excuse me. Moreover, the above-mentioned coordinate transformation can be combined. We show the result of this combination as a generalized transformation expression in slide number 7. Here we use symbol to define conjugate hypercomplex number. These transformations are linear ones. On the other hand, it allows to make transformation more simple but from another one. It can be obtained a quite nonlinear transformation if one considers transformation terms as some time-dependent nonlinearities. To make transformation more complex, it is possible to use nonlinear transformation expressions, which are not shown here, but depend on transformed variables in fully nonlinear way. The combination of the previously obtained first-order equation for the considered system with the generalized transformation equations makes it possible to write down equations for the transformed system and to solve the second problem of our task. From the control theory viewpoint, one of consider these equations as a plant observer equation. By changing observer parameters and algorithms, one can get different chaotic attractors for the one chaotic system. It is clear that such a system is the system of differential and algebraical equations. It is quite hard to use these equations for the system analysis, especially when observer parameters are time-dependent ones. That is why we solve the observer equation and use its solution to define the derivative of output signal. In the case of time-dependent observer parameters, this derivative is quite complex and allows us to widely change the system output. We use this derivative to write the chaotic plant equation in terms of the observed output variable and observed variables parameters. A similar equation defines system dynamic with constant observer parameters. You can see right-hand function for both cases in slide number 10. Analysis of these functions shows that shift transformation generates three terms which change system dynamics and make a background to define time-dependent chaotic systems. Meanwhile, rotation and compression terms only gain system output. Thus, we solve the third problem of our paper. Now, we show the benefits of our proposed approach by considering the well-known Lorentz system. Its equations are shown in slide number 11. We use system state variable as the imaginary components of the state variable Q, as well as right-hand expression of Lorentz equation to define right-hand nonlinear function f. Both nonlinearity f and variable q are defined by using quaternions. This approach gives us the possibility to define the Lorentz system dynamic by using the first-order differential equation, which is defined in the quaternion state space. This equation is defined the continuous time domain, but it can be easily written in the discrete time one to perform numerical solution. In slide 12, we show discrete time recurrent solution for Lorentz equation, which is obtained by using backward difference approximation of derivative operator. You can see the Lorentz attractors, which is the solution of the above-mentioned equation. This attractor is defined in the quaternion hyperspace with the compacted real axis. It is clear that the given simulation results are fully content with well-known ones because no transformation were performed. Thus, we prove the correctness of our approach. Views shown in slide 13 continues to perform Lorentz system transformation. Their terms are selected in a random way and can be other ones as well. Due to simulation, it was found that the both rotation quaternion and scale 1 should be multiplied with state variable. Thus, both of them gain this variable. To make a difference between these quaternion, we define scale quaternion from the desired scale terms and for each axis by solving appropriate equation which can be found as multiplication of two quaternions. The chaotic attractors of the transformed system is shown in slide 14. It is clear that the transformed system and the initial one have different attractors and thus produce different oscillations. This fact proves that possibility to use the observer equation to change chaotic system dynamics. You can see this conclusion in slide number 15. The main of them is the proven possibility to use the hypercomplex number to change chaotic system dynamics and produce novel chaotic oscillations. These oscillations can be used as the basic to design secure data transmission channels. Thank you very much for your attention.